and its multiplication as memory. And
debated topic. So on that point, I'm going to pass you over to Shabazz. So many thanks, Shabazz.
Thank you very much, Jason, for a very kind introduction. So as Jason already mentioned, that I am going to talk about superconducting spintronics, mainly focused on the contributions that we are doing at Cambridge, and those already also happened in the Cambridge. So in fact, the Cambridge is contributing in this programmable computing since the beginning. For example, here is the picture of the first calculator developed by Renwick and Sir Wilkins in 1947. So this calculator was so huge that it really need a full one lab. And this system was working on mercury delay lines as memory, and derated vacuum tubes for logic. So this system was consuming about 11 kilowatts energy, and its multiplication time was about 6 milliseconds. So since then, we know that the progress in computing and in computers and computers, so it was so rapid that it also actually reduces the sizes of the computers. What on the other hand, it actually also, you could say that the increases the size of the data centers. So nowadays we have the data centers, as you can see here. It's a huge data centers. So about 10 to 15 years ago, that these data centers, they were mainly processing the emails or you can say storing the information. But then with also processing the information, so the requirement and the size of the data center was actually exponentially increasing. At this point, all over the world, we have about 500,000 of data centers. And by the next year, or maybe you could say that at the end of this COVID year, that maybe it is already actually double. So in these data centers, the main technology that we are utilizing is the CMOS, a complementary metallic oxide semiconductor. So this technology is working so far for actually the energy storage and processing there. And then the increase in the requirement of the data centers, or the number of data center, is here. You can see in this graph that it is actually linearly increasing every year, and it will, of course, will continue increasing. And this increase in the number of data centers also increasing the requirement, or you could say, is an increase. There is an increasing demand of the electricity for running these data centers. And for example, in to run these data centers, we need about 4% of the total electricity generated within the Europe. And out of that 4% electricity is only used to keep these data centers cool. So then it means that we are in fact not only consuming a lot of energy, but we are also contributing in energy dissipation, which is contributing in the carbon emission. So to actually, because as I already mentioned, that these data centers, they are working with CMOS technology. So to address these questions related to energy efficiency, that what could be the role of spintronics? For example, the electronics that actually exploiting the spin. So this here I will show you the timeline of the spintronics, that we know that the spintronics was actually initiated with the observation of giant magnetoresistance by two Nobel laureate, Professor Grunberg and Professor Fact, in 1987. So then, based on their observation of giant magnetoresistance in 1991, the spin valves were developed. So where we actually use two ferromagnets and non-magnetic, which is sandwiched between these two magnets. So then in this structure, the transport properties are actually dependent on the spin alignment of both of these ferromagnets. So you can switch your resistivity by switching the magnetization parallel to the anti-parallel. So then in 1999, then there was another, actually the phenomena that is the spin transfer torque, means the switching of the magnetization through the spin transfer torque was also observed. So this was also very important, that you need, you can actually push a spin polarized current, which can actually transfer the momentum and can switch your magnetization from one direction to the other. So it depends that in which direction your polarized current is going there. So then I guess, yeah. So, and then not very late in 2006, the spin Hall effect was observed. So this spin Hall effect, what we do, that we do have, for example, a ferromagnetic layer, and which is actually connected with a non-magnetic normal metal layer. So by pushing the current in the ferromagnet, that can actually give the spin imbalance, a spin current in the normal metal, and it can actually induce the voltage, meaning that this is because of the spin splitting in this normal metal, which is actually giving us the charge imbalance, which is inducing the voltage, which is coming because of this you can say the spin dependent transport at the interface. So this spin Hall effect was observed in 2006, and then recently antiferromagnetic material-based spintronics was also initiated, where antiferromagnetic materials can be utilized for switching from one state to the other. So this could also be actually utilized for memory devices. So currently, we already have this STT MRAMs. So STT means spin transfer torque based MRAMs. Those are already actually, you could say, available there. And then now let's have a look that whether they are efficient or not efficient, and what could be the actually the you can say the competition with respect to the CMOS technology. So as we see that we actually in this spintronic devices, what we do, we are actually switching the state from parallel to anti-parallel or anti-parallel to parallel state. So for this process, the minimum amount of energy which is actually you could say given by the magnetic anisotropy, and this energy at room temperature is about 10 raised to power minus 19 joule, and at low temperature it would be minus 21 joule. But in case of the CMOS devices, that actually corresponds to is of the order of 10 raised to power minus 16 joule. And here we can see that it is actually four to five orders actually, you could say, more efficient this is spintronics. What, as we already actually I mentioned, that for switching, particularly the electronic switching, we need spin current. And for generating spin current, we need a large charge current. And that charge current, which we actually need for spintronic devices, it dissipates, of course, the large current will dissipate the large amount of the heat energy, which corresponds of the order of minus 15 joule. And this dissipation, of course, again, the loss of the energy, and it could also contribute in carbon footprints. So then now we can think that can we do this spintronics with a current that could be dissipationless, meaning that sort of a zero resistance, and the zero resistivity we could achieve in superconducting materials. So can we do spintronics using superconducting materials? So yes, it could be possible. So then here you can see that the IBM recently actually started this 3 billion project to do superconducting computing, meaning developing the computer based on superconducting technology and based on superconducting devices. But on the other hand, we can also do, for example, this computation using single flux quantum. What in single flux quantum technology, we need microsquares. So then this sizability could be an issue there. So then let's have a look on the timeline of superconducting spintronics. The superconducting spintronics, in fact, started with the idea of Josephson junctions that was actually first given by Professor Brian Josephson and from Cambridge. So the idea is that if we connect two superconductors with a barrier, and that barrier can be an insulating, and through this insulating barrier, we can tunnel the superconducting, you can say, the particles from one side to the other. And so in this way, we can develop a junction, and that junction is the transport properties of this junction is depending on the phase difference of these two, let's say, the superconductors. And then in 2001, there was a new development, and that development was the pi junctions. So pi junctions means that what we do have, we have a superconductor. For example, in this example, that was done by Ryazanov in Russia with the collaborations of Leiden, the Netherlands, my previous group. So there, they actually connected two, they have two superconductors, niobium, and a copper nickel ferromagnet, which is a weak ferromagnet. It is actually providing a weak link between these two superconductors. So here you could see that the phase of the system is oscillating, is oscillating from 0 to pi by changing the thickness of the ferromagnet. So this idea can also actually can be utilized to develop phase batteries. So then in 2004 at Cambridge by the Professor Mark Blamer, so they developed superconducting devices where they do have two superconductors. And here the barrier is in fact like a spin wall, that we do have two ferromagnets and then there is a barrier in between. So the transport properties of this device depends on the alignment of magnetization of these two layers. And here you can see that these black circles, they are representing the critical current of this device, which is actually switching from anti-parallel to parallel state. And this red one, it is the resistance of the system. So you can see very clear switching. So here, the one point, so this kind of technique, a technology, you could say, can be utilized to develop cryogenic memory devices. And here, the thing that you may note that both of these works, there is the main thing is that the charge transport. So these are based on the transport of the charge rather than the spin of superconducting particle. When I say superconducting particle, that means the Cooper pairs. So then something very interesting happened in 2010, where Professor Robinson, he observed spin-polarized supercurrents. So in this spin-polarized supercurrents, they used multi-layer ferromagnets as a barrier between two superconductors, which is generating the spin-polarized supercurrent. And in my next slides, I will go in more details that how we actually can do this. And at the same time, there was also two more groups, one from Leiden, where I was actually doing my PhD at that time, and I was the part of that project. So I was trying the same kind of things with half metallic ferromagnets. And the third group was from Michigan State University. So they also utilized the multi-layer ferromagnets and observed this spin polarized superconductor. So here in this figure, you could see that if we are using the single ferromagnetic layer, then critical current in the device can actually die off quickly with the increase in the thickness of the ferromagnet. But if we do have multi-layer ferromagnets, then it actually is not dying off. So it's actually staying even for a thicker total ferromagnetic barrier. So then in 2014, again from the Cambridge University, so there the spin selectivity of the spin triplet Cooper pairs was actually observed, where multi-layer ferromagnetic and a superconductor system used. So this system is like, you could say, a superconductor ferromagnet bilayer like system, but this ferromagnet is a multi-layer. So, and the last layer is an anti-ferromagnet, which is fixing one ferromagnet, and other ferromagnet, which is a permalayer, you can switch its direction for observing spin selectivity. And then this superconducting devices based memory devices were developed in 2018 by North Grumman Corporation. So there they utilize this charge-based technology, and they are actually reading or writing the information using these microsquids. So again, these are the microsquids. So then scalability could also be an issue in these devices. So then now the question that how we can induce or put the spin in the superconductor, or we can have this spin polarization with the zero resistance for our charge current. So here, let me give you an example of a superconductor. That in superconductor, we do have a Cooper pairs, as you know, that both have a opposite spin. So total spin of a Cooper pair is 0. And if we connect with a ferromagnet, but there the spins are aligned, and we have a spin polarization, because in the ferromagnet, there is a spin splitting. At the Fermi level, we have different spin density of state for spin down and spin up. And if we put this Cooper pair in this ferromagnet, then we actually, our Cooper pair can gain the momentum because of this mismatch. So total is not 0. So we are getting some, our Cooper pair will get additional momentum. And because of this additional momentum, the correlation which is induced in the ferromagnet will actually have the additional oscillations. And these oscillations are also the change in the phase of the correlation. And secondly, that the exchange field of the ferromagnet will kill this kind of a superconductivity, because the ferromagnet would like to align the spins. So this superconductivity will die off very quickly in a ferromagnet, but within few nanometers, even for a weak ferromagnet. And then here, one more point that I want to raise here, that here at the interface, what's happening, that we do have a spin singlet Cooper pair, but we do have this spin splitting. So because of the spin mixing at the interface, we can also have spin triplets, but these spin triplets are with zero alignment, meaning that their alignment is perpendicular to the quantization vector. So these are also actually will die off quickly within the same range as the spin singlet will die off. So then in this system, if we connect another ferromagnet to the other side of this bilayer, so this is now a ferromagnetic Josephson junction. So in this ferromagnetic Josephson junction, what could happen that here is the work formed by Professor Robinson in 2006. So they are changing the thickness of this central ferromagnetic layer and then observing the oscillations of the correlation inside this ferromagnet, which was the permalloy and cobalt. And here is the figure, the photo of the device. So main junction is here, top superconductor, bottom superconductor, and in the center we do have a ferromagnet. So here you can see that in both cases, cobalt and permalloy, you can very easily observe the oscillations in these superconducting devices. So now these ferromagnetic devices combined with the spin valves, so we can have Josephson memory devices. So here in this example, because this is again depending on the charges, meaning that the transfer properties, the spin-dependent transfer properties of this device is actually being utilized to develop the memory devices. So that's why we call them the charge-based memory devices. So you can see that when we do have a parallel here means the ferromagnet number one, which is permalloy, and the other one can be cobalt. So the Quersor field of both of these ferromagnets is different. So you can easily switch the magnetization of permalloy at a very small field, like 5 millitesla in this situation. So here you can see that in case of parallel and anti-parallel, you can have a different, you can say the critical current in this device. And this idea is being used in these Northrop Grumman memory devices. So now, if we want to have a fully spin polarized supercurrent, what should we do? So in that case, as we have already looked, that we can have M is equal to 0 spin triplet. And these spin triplet Cooper pairs can be switched to equal spin triplet Cooper pairs, where the magnetization, you could say the spin alignment of Cooper pairs is parallel to the quantization vector. And this can be achieved if we do have some kind of magnetic inhomogeneity at the interface. And this magnetic inhomogeneity actually rotates M is equal to 0 spin triplet two parallel spin triplet Cooper pairs. Those are actually providing us fully spin polarized supercurrent. And if we do have these fully spin polarized Cooper pairs, now you can see that the exchange field of a ferromagnet should not be enemy of these Cooper pairs, and these Cooper pairs should be able to stay for a long length inside the ferromagnet. For an example, that they can actually reach up to 40 to 60 nanometers in the cobalt, which is a sort of the spin flip length. Because now the exchange field will not kill these Cooper pairs. The spin flip scattering can kill these Cooper pairs. So how we can achieve magnetic inhomogeneity? The magnetic inhomogeneity can be achieved using having a ferromagnetic domain wall at the interface, or non-collinear magnetization, meaning that we have a multiple ferromagnetic layer. Those have a bit different magnetization alignment. So this technique is nowadays mainly being utilized in by the different groups. And then in addition to this, we can also have magnetic inhomogeneity even if there is some disorder at the interface. That can also give you some magnetic inhomogeneity, which can switch your spin singlet Cooper pairs into spin triplet Cooper pairs to achieve fully spin polarized Cooper pairs. So here I again give an example of the work done by Professor Robinson. So here you can see that when we do have a ferromagnetic Josephson junction, but here we have only
Now, you have 3 minutes left.
Yeah. Okay, so we have a cobalt, But here we have additional layers. Those are actually giving spin activity to generate spin polarized supercurrents. So you can see they can actually stay for a longer length. And then another very interesting work, which is the spin-based memory. So it is our unpublished work. And here we have, again, the same kind of the device as I introduced, that we have a Josephson junction, but in the barrier is the spin wall. But we are generating here the spin polarized current. And that spin polarized current can be actually, you could say, can be switched from the lower critical current to higher critical current by just switching the magnetization of one of the ferromagnetic layer. So this can be used as spin-based memory devices. And then the last point here is that in addition to the spin polarized charge current, we can also generate a pure spin current. That could be pure superconducting spin current, that we do have a ferromagnet. We can pump the spin which interact with the spin orbit coupling of this heavy metal like a platinum, and it generates the spin polarized, pure spin supercurrent in this system. So this is our the current work from Robinson's group at the Cambridge University. And now here I would like to summarize my talk. The superconducting charge memory is under active development into a technology, and by mainly the Grumman. They are actually developing it very actively there. So then triplet spin current generation is already well understood. And then pure spin supercurrents have also been demonstrated, as I showed in my last slide. And sorry, I couldn't have much time to explain in more details. And then this actually all observations and understandings actually paving the way to superconducting spintronics, having, you could say, dissipationless spintronics, energy efficient spintronics. So thank you very much.
So thank you very much, Shabazz. I believe I'm the chair. Would anyone like to ask Shabazz any questions about his presentation? So you could either put a question in the chat or you could put your hand up.